Okay, so we're going to talk about phase changes, okay? I want you to remind yourself of the graph that we looked at a while ago, right? You have like ice, and the ice heats up, and then the ice melts, and it turns into water, which heats up, and then the water boils, and it turns into steam, which can heat up, all right? And remember, on this side was temperature, and this side was heat. Okay. So this graph becomes important because we need to remind ourselves that during a phase change, there is no temperature change. Okay. So during a phase change, the temperature doesn't change. All of the heat goes into changing the states, not the temperature, right? So that heat goes into turning it from a solid to a liquid, or from a liquid to a gas. All of that heat energy goes into that. So the formula Q equals MC delta T is only for temperature changes. It's only for this portion of the graph, this portion of the graph, this portion of the graph, okay? That's where Q equals MCT counts. During the phase changes, we actually have another equation that we're going to talk about today. So this is heat involved in phase changes here. This is the same picture, but I tried to pick one that had a lot more stuff in it, right? Here we go. Here's the solid, liquid, and gas portions. That's where the Q equals MCT exists on those graphs. Here we have it melts, it vaporizes, in this direction it condenses, and it freezes. We call this portion right here fusion. Okay, the word fusion basically means melting, and we call this portion vaporization. You could have the word boiling here. That's really fine. All right, so keep this graph in mind as we go through here. Melting has its own equation. Q heat melt, Q melt equals delta H fusion. This is read as the heat of fusion times the number of moles of the substance. All right. The heat of fusion is, by definition, the amount of energy required to melt 1 mole of a solid. There is a reference table attached to this chapter in the notes. You can go to that reference table and you can find values for heat of fusion. It's also attached to the homework today to make it easier to find. The heat of fusion for water is on the back of your periodic table, and you can find it just about anywhere. It's 6.01 kilojoules per mole. And the reason I give you water is because water, we use it a lot. All right, the next one is boiling or vaporization. So Q boil equals the heat of vaporization, or the heat of, sometimes it's just written the heat of vap, times the number of moles. The heat of vaporization for water is 40.7 kilojoules per mole. Now you'll notice right away, the heat of fusion is 6, the heat of vaporization is 40. Remember way back when? I said over and over again that the heat of fusion, it takes less energy to melt ice than it does to boil water. There it is mathematically, 6 versus 40. It takes less energy to melt than it does to boil. So here's some math problems, right? They're kind of plug and chug. How much heat is required to completely melt 450 grams of ice? Now, Q equals MC delta T was in grams, but this one requires moles. So you have to know something right away. You have to understand that ice is water, which is H2O, And the molar mass of ice is 18 grams per mole, right? Because we've got two hydrogens attached to an oxygen, which weighs 16. Because step number one, you've got to convert 450 grams of ice into moles of ice. I told you stoichiometry was never going anywhere. This is more stoichiometry, grams to moles. Now remember, this is just, I just kind of shortcutted it there, but you have 450 grams. For every 18 grams, there is 1 mole. And that's where I got the 25 moles. Okay, so step one, you got to find moles. Step two, plug it into the heat of fusion equation. Q melt equals the heat of fusion times the number of moles, which equals 150 kilojoules. I'm maintaining my sig figs. The only sig figs that I'm worried about are these two, because these were the original measured values in the formula, and I end up with 2 sig figs. The second thing that makes this equation different than Q equals MC delta T is that when you're done with Q equals MC delta T, you usually get an answer in joules, and this is in kilojoules. And that'll come up in a second, that you'll have to pay attention to that. This is, same thing, except now instead of melting it, now we're condensing it. All right, so a few things. First of all, you need to use the heat of vaporization. All right, this is given to me in moles. So here's moles. And then my answer's in kilojoules. I want to point out to you the negative sign. The negative sign simply means that I'm moving in the other direction. Instead of adding heat to vaporize it, I'm removing heat to condense it. All right, so Q condense equals the heat of vaporization times the number of moles. Condensing is the opposite of boiling, and like I said, that's why the negative sign will be there. Now, as a warning to you, you will not always see this as a negative value. Don't panic. Sometimes it is, sometimes it isn't. It's just whether they want to show you that heat is being removed or heat is being added. I think it probably should be there, but it's not always. Now, most of the time we're working with water, but let's say we're working with something else. You may have to look up its heat of vaporization. Here's ethanol. Ethanol is, sometimes what's in hand sanitizer. It evaporates off your hand very quickly. So it does have a smaller heat of vaporization, and that makes sense. So it says, how much energy do you need now to boil 6.9 grams of ethanol? Step one, you've got to convert the grams to moles, right? So you've got 6.9 grams, and then you have to figure out the molar mass of ethanol. There's 2 carbons, there's 5 hydrogens, there's an oxygen, and there's a hydrogen. Nowadays, you can just say, hey, Siri, what's the molar mass of ethanol? And usually she's... Here's what I found. Okay, so she found the molar mass for me on my watch, all right? So you can do that if you've given up at this point. 46 grams per 1 mole, all right? 0.15 moles. Then I'm going to plug it into that same equation, being sure to take into consideration it is not water, so it does not have a heat of vaporization of 40. It's a little bit lower. I had to look it up on that chart, and I get 5.8 kilojoules. Now this last problem, this runs through a couple steps. All right, you have to remember what we did before with Q equals MC delta T. You can't forget that, and what we are looking at now. In order to do that, you always have to have the graph in mind, right? We warm up the ice, we melt the ice. We warm up the water, we boil the water, we warm up the steam. Okay? It says that a glass of water is 100 grams of water, and it's at 22 degrees Celsius. So guys, it's here on the graph. How much energy is required to boil this? Well, before I can boil it, I have to heat it up. I have to get through this portion of the graph. That portion is a Q equals MC delta T portion of the graph. From there, then I can boil it. I can go through this portion of the graph. And that portion of the graph is the Q boil. All right, so I have to do really two equations. And what I like about these is that it makes you think from, beginning to end of what this means. So I'm going to start with the Q equals MC delta T. All right, I've got 100 grams of water. It is liquid water at this point, so 4.18 joules per gram. The delta T always tricks students. You're going from here to here. Guys, I know that it's going to 100 degrees Celsius because I know that water boils at 100 degrees Celsius, and so should you. So that's where I got this 100 degrees. I know I'm going for boiling. So 100 degrees Celsius minus 22, that's what it started at, is a change in temperature of 78. So to heat the water, it's going to require 33,000 joules. But I'm going to go ahead and convert that to kilojoules because the other part of my problem is in kilojoules. So I did that kind of right away. So now I've reached, the water is now 100 degrees Celsius. Well, now I have to boil the water. So in order to boil the water, I move on to Q boil. That's the heat of vaporization times the number of moles of water. So now I've got to do some converting again. I've got to say I've got 100 grams of water. Water is 18 grams per 1 mole. So I need to find out that I've got about 5.56 moles of water. And I can plug it into this. This is from the chart. That's the heat of vaporization, 40.7 times the number of moles. That's how much energy it takes to boil it. You'll notice it takes a lot more energy to boil something than it does to heat something. That's something that we can start looking at, thermodynamics. And then you just add those numbers together. How much total energy does it take to move from 22 to boiling? It takes this. All right, 33 kilojoules plus 226 equals 259.